Hi, welcome to another lecture on Calculus 2. Today's topic is parametric curves. So, easiest way to distinguish curves from parametric curves is by these two words. Curves look like pictures. Parametric curves look like animation. So, for example, if I say I'm going to walk on this track, okay, I'm specifying the location I'm going to be, but how about being more precise? Suppose I say on this track I am going to start at, say, this point. After 1 second perhaps I'll be here, another second maybe I speed up, and then I speed up again, and then after that maybe I slow down. So this was time 0, time 1, time 2, time 3, time 4, maybe I speed up again, 5, and so on. So moment by moment I'm giving the location as to where I'm going to be, as opposed to in this case that I'm just saying I'll be on this circle. So what we are going to do today is to learn how to give detailed information about the location of an object. Most common way to do this thing is by parametrizing with respect to time. Most common variable we use to specify the position that we are going to have is going to be with respect to time. But of course you can also use other tools. For example, you can use angle. So for example, if you have the minute handle of a clock and it is turning around, you can say at what its location is going to be when it's making a 30-degree angle with respect to 12 o'clock and such. You can also use distance to specify the location, like how far has somebody walked by the time it had arrived at a certain location. So let's go ahead and imagine that our variable is the time and see how we are going to go ahead and analyze data in this way. Best way to approach this thing is to perhaps do some exercises. So suppose we say x of a location of an object or a particle is given by say 1 minus t squared. So we are using time t, and the location y for the y coordinate of an object perhaps is given by 2t minus t squared. And we want to track this object for t ranging from, say, -1 to 2. So what we have here is an example of a parameterization, and we could use t for anything. Here, easiest way to talk about it is in terms of time. How are we going to approach this problem? The best way to approach this is to go back to the graphing topic that we had in Calculus 1, and in this case make a table with 3 columns in it. So T is our basic column, and then we have the column for X, and then another column for Y. So T starts at -1, and we want to go as far as 2. So on the T column, I am going to go between from -1 to 2. Well, obviously we are going to go across 0 and then 1 and then and 2. But of course there are many other time points like -0.5, 0.5, 1.5, and as your patience allows, you can fill up this column with more and more time values. So at -1, what is my x? Well, I put -1 in my formula, and I see that 1 minus -1 squared is going to be 0. How about y. My y value is going to be minus 2 and then minus 1, so that's going to be minus 3. So we start plotting. So I have my coordinate system here, and it looks like our starting point corresponding to time equal to minus 1. I am at location minus 3. So that is my starting point. So the curves that we draw in this way, they have a starting point and an ending point, or sometimes they are referred to as initial point and a terminal point. So typical language used, start and end, or initial terminal, or similar language. Okay, first let's go ahead after the easiest point. It's recommended you use a calculator, but with these friendly numbers we should be okay. So at 0, my x is going to be 1 and my y is going to be 0. So I have arrived at the following location. So I might as well specify what time it was that I was here. So it was time minus 1. This was time 0. How about the time 1? At time 1, x has become 0 again, and y, 2 minus 1, is going to be 1. So at time 1, my x is 0 and my y is 1. So I am at this location. At time 2, what happens? At time 2, my x is minus 3 and my y is going to be 4. Minus 4, I'm going to be 0 again. So at time 2, my x is minus 3, 2 and minus 3, and so this was time 2. So based on this rudimentary data, what do you think is happening? It looks like we are going from this point, that was a starting time, to this one, and to that one. So it looks like we are going through such a trajectory. We kind of guessed that if we had started earlier, like minus 2 probably would have been here. And if we go past time 2, we probably continue in that trajectory. Well, we might wonder, well, what kind of a curve is this? So we have the parametric curve, and this parametric curve has a start and end. It has a sense of a flow to it. So you see that sometimes they put arrows indicating as time progresses which direction are we headed. Like, are we going this way or that way? Are we going clockwise or counterclockwise, or whatever the case might be? So you always want to indicate the start and end, and put arrows on your curve to indicate in which direction you are flowing. Next question, well, what kind of a curve is this? Well, that will require some additional work, perhaps quite a bit of work. This turned out to be a parabola that has been twisted by some angles, and maybe most of the parabolas that you have looked at were either vertical or horizontal, and this one happens to be a slanted one, but it does turn out to be a parabola. However, we are going to put that aside and go after some other questions here first. And if we go to the topic of conic sections, we are going to talk about the parabolas as well. So this was one example. The next, we might have the question of, well, what kind of a curve is this? Let's go ahead and practice that on something that's going to be a little bit easier. So here is, for example, another problem that x is given as t squared minus 3, and the y is given as, say, t plus 2. So as time moves, x is following that and y is following this one. And let's suppose that our time is running from -3 to 3. So the question is, what's the picture? The way the question is typically worded is, they say eliminate t and find a Cartesian equation. Eliminating t means what? Means connecting x and y to each other without the middleman of t. T here is a middleman that decides what x is going to be and y is going to be. But now we are going to tie x directly to y without the presence of t. In this case, it's going to be kind of easy. You figure out what t is from one of the equations. T is equal to, y minus 2 from here, and put it in the first one. So x is equal to y minus 2 squared minus 3. So here, if you want to simplify, it becomes y squared minus 4y, and then 4 minus 3 is going to be plus 1. So x is equal to y squared. Do we remember what kind of function that is? That's of course again a parabola, but this one we can easily say that it is a parabola that's opening toward the right. So we eliminated t and we obtained a Cartesian formula that's just connecting x to y. We have lost the connection of, well, at what point, in what fashion are we traveling on this parabola? We are not having an indication of a speed or anything like that. We just know that we are traveling on this. So what are we going to do with the limits on t? Well, at t equal to -3, if I put t equal to -3 here, I get x is equal to 6 and y is equal to -1. At t is equal to +3, x becomes, again it becomes 6, and now y has become 5. So this is going to be the start, and this is going to be the end. So whatever that curve is, we are going to cut it short. We are going to have a starting point and ending point. Now you might be wondering, well, what is that curve? Well, this is quite a bit easier than the previous problem. We might as well go ahead and answer exactly what is the answer. So let's go complete the square so that I'll write it in a standard form. To do that, I add 3 to both sides. So I'll have x plus 3 is equal to y squared minus 4y plus 1 plus 3. Why did I do that? Because now right hand side is a complete square. Now we are going to appeal to an idea from college algebra. We had the idea of transformation of curves. That is, if you have x equal to y squared, well, that's a curve that's very basic and you know it very well. That's just a parabola that opens toward right. When you replace x by x plus 3, it means your picture is going to move left by 3. When you replace y by y minus 2, it means your picture is going to move up by 2. So what we have to do is to take this picture, push it to the left by 3 units and push it up by 2 units, and that's going to be our new picture. So new picture, 3 to the left, perhaps something like this, and 2 up, perhaps something like this. So this is going to be the tip of the parabola, and then we are going to have one point up and down here, and kind of like this. So down here is going to be the point with the coordinates 6 and -1 that we found here. Sorry, 6 and -1 that we had here. That would be a starting point. And up here is going to be the other point, 6 and 5. That's going to be the terminal point or ending point. So we have a parabola that travels in this direction, turns around here, and then goes toward that destination. Okay, so that was another example. Sometimes instead of using language of time, we might use the language of angle. So suppose I have x is equal to cosine of, now it's customary to use theta for an angle, but it could have been time. It doesn't hurt either way. Suppose theta ranges from 0 to pi. What does the curve look like? Well, this is a very famous example. You see it in lots of different classes. For example, in physics, you see it as mentioned as a simple harmonic motion, and in your calculus classes, it comes as a description of a portion of a circle. So what do we do to see what's happening? We might as well make a table. So here my table has theta and x and y in it. We might start with very friendly angles, 0, pi over 2, and pi. Later on we might get more ambitious and put more angles in between. But at 0, x cosine of 0 is 1, y sine of 0 is 0. So that would be, let's say this is the point 1 and 0 at theta equal to 0. Now pi over 2, cosine of pi over 2 is 0, sine of pi over 2 is 1. Now we can think about the theta as the angle by which we are rotating. So instead of using time as an indicator of where we are, we might use the angle by which we have rotated, and then we are specifying where we are right now. So now we have come to the location 0 and 1, and this has happened at theta equal to pi over 2. How about theta equal to pi? Cosine of pi, we know it's -1. Sine of pi, we know it's 0. So if I continue going, so my angle now is going toward pi. That point is going to come to this point. It's going to be at the point -1 and 0. And here theta has become pi. So the trajectory for our particle or person is that it came here and then stopped at this location. And this was the starting point, this was the terminal point, and these are direction of the movement on this trajectory. So well, what if somebody wanted to eliminate theta here? How would you eliminate theta? Well, you remember from your trigonometric identities, if I square them and add them up, so x squared is cosine square of theta, y squared is sine square of theta, and if I add them, I get x squared plus y squared is equal to cosine square plus sine square and that is just 1. So what we get is x squared plus y squared equal to 1. However, because of this restriction on theta, my parametric curve was this half circle. This one, x squared plus y squared equal to 1, it completes the picture and gives the full circle. You have to figure out the beginning and end of the curve for yourself. Okay, so that was that example. Now let's go ahead and look at something else. Suppose I change the so-called frequency, that now I have x is equal to cosine of 2 theta, and y is equal to sine of 2 theta. Again, I say let's take theta to go as before between 0 and pi. Let's make our table here so that I have room to expand it a bit. So I have theta. Maybe I make 2 angle columns. So if there's a theta, and then you double it before you use it, and then out of that you make your x and you make your y. So what we are feeding to sine or cosine is just 2 theta. Let's again use our friendly angles, 0, pi over 2. Let me make more room here. Now our theta, if you are choosing 2 theta first, our theta is of course going to be half of these values. So this is half of 0, half of pi over 2, half of pi. So these are theta values. We are doubling them to get these values. Now we are feeding them to cosine and sine to figure out the x and y. So x is cosine of that, so that's 1 and this is 0. X is cosine of this, so that's going to be 0 and this is going to be 1. And here x is cosine of pi, so that's minus 1 and this is 0. Now we wonder if theta keeps going, the limits of theta going as far as pi. So if I go all the way, let's go to so here I have 3 pi over 2. This is going to be 3 pi over 4, and then this is going to be, of course, 2 pi. Half of that is pi. Cosine of 3 pi over 2 is of course 0. Sine of that is minus 1. Cosine of 2 pi is 1, and the sine of that is 0. Let's go ahead. So we let theta run from 0 to pi, and these are x and y values. If I graph them, what do I get? So first one is 1, 0 is, let's say this is 1, 0. Then 0, 1, here is say 0, 1. Next is minus 1, 0, so I have come to minus 1, 0. Next is 0, minus 1. 0, minus 1 is down here. Finally 1, 0, we have come back where we were. So we started here, we came to this, say, point north, and then this one, and then south, and back to east or whatever that point is. So notice that our angle ranged from 0 to pi, theta ranged from 0 to pi, but since we are doubling it before feeding it to x or y, even though theta went from 0 to pi, we went through the entire circle. We went through all of this thing because now 2 theta went from 0 to 2 pi. So one thing we learned here is that you can manipulate the speed through this number that you see here. Now let's go for the final act today. Let's look at a famous and interesting problem referred to as cycloid. The curve that we are going to study comes up in different areas of mathematics and physics, is very famous and has a history behind it. You want to read the text about Brachistochrone and see what the story is about. So what's the question here? The question is, suppose we have a tire or a coin that is resting on the page, or a tire on the road. Now consider a point on this tire. Suppose you take your magic marker and put a red dot there, or stick a pebble in the tire at that location. Now you let the car to move, so the tire is going to rotate. We are going to assume it's going to rotate on the road without skidding. So what happens to this point? So of course, as you move, the circle turns, the tire turns. So it comes here, for example, and by that point, by that time, the pebble has moved to some other location, and then again, as you move the tire, this starts to go up, and at some point it reaches the height of the tire, and then after that it just comes down again. So this curve is what is called the cycloid. And the question is, what is the parametric equation of this curve? So let's assume that the radius of this tire is just r. So r is the radius. And then we want to find out the coordinate of this point. That is, this point is going to have some x and y. And we want to find out x and y in terms of some parameter. The easiest parameter to use is how much this tire has rotated. So for example, from this location to the next location, it has rotated by a certain angle. That angle theta, I'm going to use that as my parameter and try to find out my coordinates. So let's draw a bigger picture. So suppose that my circle has come here. The point was originally at this location. Now the circle or the tire has turned, and the point has come to this location. This is the center of the tire, and the angle by which we have rotated the tire is this angle theta. Now, a major observation. Since this tire is rotating without skidding, the amount of displacement that we have here is exactly equal to length of this arc on the tire itself. They are both same numbers. Now let's remind ourselves something from trigonometry. If I have a circle and the radius of it is r, and here central angle is theta, what is the length of the arc that is right in front of it? What's the length of this? Let's call it L. What's the connection between these three quantities, L, r, and theta? If you remember from your trigonometry, L is r times theta. That's actually the definition of the angle theta in radians. So if this is r theta, and then so is this is also r theta. Now this distance is going to be, since this is r and this angle is theta, this opposite is going to be r sine of theta. So r sine of theta plus whatever this quantity is going to be same as r theta. That means this x is r theta minus r sine of theta. Did you follow that? So this is r sine theta, and this whole length is r theta, and so our x is this quantity. How about the y? I want to find the y as well. Well, this one is r cosine theta. The whole radius is r, so what is left here is r minus r cosine theta. So y is r minus r cosine theta. Let's paraphrase all of these things. So what we have here, x, I can factor r out of it, r times theta minus sine of theta, and y is r times 1 minus cosine theta. The cycloid is gonna go through one cycle of it for angle from 0 to 2 pi. I encourage you to read the history of this thing. So it also comes up under the Brachistochrone curve. Was a very famous question proposed as a challenge by a mathematician by the name of John Bernoulli. And the question he had was the following: suppose I want to design a slide, okay, just like the slide you have in the park. So here's a kid at the top of the slide, and he wants to go down here. From here he wants to go down here. The question is, how should I design this slide so that this kid comes down in the shortest amount of time? Should I have just a straight slide? If I want to curve it, how much should I curve it? Do I curve it a lot at the beginning and then make it flat later on, and so on? It turns out, that's what John Bernoulli showed, that the most optimal curve here is the inverted cycloid. That is, if you take that cycloid we're talking about, turn it upside down, this is the shape that's going to have the most fun for the kid, meaning from any point of it to the bottom of this is going to be, the kid is going to slide down in the shortest amount of time. Okay, so a lot of history there. Again, I encourage you to go ahead and read it. Until next time, good luck and God bless.